This is where it all comes together. These are the four fundamental subspaces of a matrix that we have studied so far. We have explored them individually, but now it's time to see how these subspaces are connected and what their dimensions are. We will also look at how vectors move from one subspace to another and the fundamental theorem of linear algebra, which mathematically shows the connection between these subspaces. So let's get started. So I will first begin the lecture with a matrix vector product. So we have seen A times X, right? The matrix A times X. Let us suppose A is a matrix belonging to A uh, three. Sorry. Let us suppose A is a matrix belonging to M cross N. That is, it is an M by N matrix. All right. So when we do A times X, so this is A, which is an M by N matrix, and this is the vector X. So this vector should be of dimension n cross n because these two dimensions should be same. So this should be n cross 1, and we will get an output vector v whose dimension is m cross 1. All right. So you see this vector, this x vector, this is coming from the this is the input vector basically, right? This is the input vector, right? And this v vector, this is the output vector. So you have a transformation. You have this xy plane, the R2 plane, and you have this x vector, and this got transformed to this v vector by the transformation A, which is an m cross n transformation, right? So this vector x is coming from the input vector space, whereas this vector v is lying in the output vector space. What I mean by that, for example, let us suppose take an example of a 2 cross 3 matrix, right? So a 2 cross 3 matrix, the vectors are coming from the R3 volume, and they are getting mapped to the R2 volume, right? R2 xy plane, sorry, the 2D space. So you can say that this is your input vector space, and the matrix A transform this input vector space, which is this 3D R cube, into this xy plane, right? So you are taking a vector. So your vector, any vector x, right? Any vector x should belong to R3, right? X should belong to R3, and the output vector v, this is x. The output vector v mapped by the matrix A should belong to R2. So here we are seeing that the matrix A is transforming a vector x which is lying in the 3D volume to the vector v which is lying in the xy plane, 2D xy plane. Okay, so this is nothing, this x is nothing but the input vector, and this v is nothing but the output vector. So this is your input vector space, this is your output vector space. All right. So this is your input vector space, this is your output vector space. Input vector space, and this is your output vector space. Similarly, there could be a 3 cross 3 matrix. You can have also a 3 cross 3 matrix which is invertible. Basically, all the column vectors are linearly independent. Then it will map vectors from R3 to R3. Okay, this is 3 cross 1, and this is also 3 cross 1. So you are basically in the input vector space is also R3 because the vector is lying in R3, and after the transformation A, the output vector space is also R3. The vectors we are lying in this XYZ volume. Okay, so why I am mentioning this? You all already know this concept, right? The thing is, we need to map these four vector spaces, right, where they are lying. So two of them belongs to the input vector space, where the two of them belong to the output vector space. Okay, So if you divide it, if uh, let us suppose you have a 3 by 3 matrix. Okay, so this is, let us suppose, your input vector space, and because it's a 3 by 3, so this is your output vector space. By input vector space and by output vector space, I mean to say from where the input vector and the output vector are coming. All right, for visualization purpose. Okay, so if it is a generic matrix, instead of a 3 by 3, let us suppose it's an R m by n matrix. Okay, then the row space, your row space, this belongs to Rn. Okay, because this is your input vector space from where your vectors are coming, which you need to map, right? So it is coming from this Rn, you can see here, because the vector should have the same dimension as the second dimension of this vector space, that is sorry, second dimension of this matrix. Okay, this is a matrix. Okay, and your column space belongs to Rm, that is output vector space. All right. So similarly, if we write down all the four spaces, right? So this is basically, this is column space, and row space is nothing but the column space of A transpose, which this we already know. So this is a subspace. It's a subspace of Rn, because this belongs to the input vector space, and this is a subspace of Rm. This is what we have studied here, right? So this is a subspace of Rn, and this is a subspace of Rm. So row space belong to the input vector space from where the input vectors are coming. The column space is nothing but the it belong to the output vector space where the output vectors are lying. All right. So you have two more. We have two more vector spaces, subspaces. That is the null space and the left null space. So we have the null space and left null space, right? So null space is nothing n of A, and left null space is the null space of A transpose, right? So null space is a subspace of Rn, is a subspace of Rn, and left null space is a subspace of Rm. That is, null space belongs here. Null space belongs to Rn. That is in the input vector space. That is Rm. This is basically Rn, right? This is Rn, and this is Rm. And the left null space belongs to Rm. Okay, so this is what a matrix is doing, right? A matrix is taking a vector belonging to Rn. This matrix M cross N, it is taking a vector belonging to Rn and mapping it to Rm. Okay, mapping it to Rm. And in this case, for example, we have taken this special case of a 3 by 3 matrix, that is a square matrix. In case of a square matrix, both the input vector space and the output vector space are same dimensional. Here n is equal to m. Here n is equal to m. Okay. So the row space and null space belong to the input vector space from where the input vector is coming. So this is your input vector. Okay. Whereas the column space and left null spaces belong to the output vector space where the output vector belongs. So this is your output vector V. All right, so you can, in a nutshell, this matrix A is moving vectors from this input vector space to output vector space, right? And these two vector spaces has these subspaces: the row space, the null space, the column space, and the left null space. All right. So let's see some visualization. So this purple plane is the column space of that matrix. The green plane is the row space. The blue line is the null space, and the red line is the left null space. Okay. So now just notice one thing. This green vector is lying in the row space, right? The green vector is lying in the green plane, which is nothing but the row space. The a time x for this vector is nothing but this pink vector. Actually, its value is pretty large, so it is going outside the plane. So let me minimize it little. See now. So this green vector, this tiny green vector, which is lying in the row space, got transformed to this pink vector, which is lying in the column space. So that's how the vectors moves. Okay, so this, first of all, these two spaces, the row space and this blue line, the null space, these are the two spaces, the row space and the null space, and they belong to the input vector space. We already seen this row space and the null space, they belong to Rn. They belong to Rn. Row space and null space belong to Rn, that is input vector space. So these two spaces, this row space and null space, belongs to the input vector space, whereas these two, this column space and this one, the left null space, belong to the output vector space. Okay, but right now I am visualizing all these in the same diagram. Okay, right now I am visualizing all the four subspaces in the same diagram. Okay, so just focus on just focus on these two subspaces, the row space and the column space. So I take one vector, this green vector. I take this one vector, this green vector, okay, which is in the row space, which is in the row space. I multiply it with the matrix, that is, I did A times X and I get V. I did A times X, I get V, that is the output vector, and it is lying in the column space. See, it is lying in the column space, this pink vector. So you can imagine that the matrix A is moving or mapping, or you can simply say it is moving this green vector or all the vectors, I mean, lying on this plane. They are getting mapped to the vectors lying on this column space, that is the purple space. I have shown you one such case in which this vector is getting mapped from row space to the column space. So if you see this yellow vector is lying in the xy plane. Basically this yellow vector is lying in the input vector space, right? Because I am showing everything in the same diagram, but yeah, this yellow vector is lying in the input vector space. After doing A times X, that is transforming it with the matrix A, it get mapped to this blue vector, which is lying in the column space. See, so similarly you can check any vector, you will get its transformed vector. So this Desmos tool, I will share the link, you can check for any vector. Okay, so this is the case, and we have already seen the null space, right? Any vector lying on the null space, any vector lying on the null space, for example this vector, this orange vector is lying in the null space. So any vector lying on the null space, after the transformation it mapped to the origin, that is the zero vector. All right, so these are the four subspaces. These are the four subspaces in a nutshell. I think some of you might have noticed that the left null space is perpendicular to the column space, isn't it? Because the left null space is the x-axis, whereas the column space is the yz plane. So the left null space is perpendicular to the column space. So this is not by accident, or this is not just for this matrix. This is for every matrix. This is in fact the property. Okay, this is one of the things in the fundamental theorem of linear algebra, that is the column space is perpendicular to left null space. All right, that is the column space is perpendicular to the left null space. Okay, space. Now it you can also see that the null space, the blue line, is perpendicular to this green plane, that is the row space. The blue line is perpendicular to this green plane, that is the null space is also orthogonal to the row space. So this is the second property. This is not by accident, or this is not just for this matrix A. It is for any matrix. For any matrix, row space is also perpendicular, is perpendicular to null space. This is the second property. That is row space is perpendicular to null space. All right. So these are the two very important properties of the four fundamental subspaces which we have studied. Some tricky questions are asked regarding these properties, so have these in mind. So we have seen the four subspaces in a nutshell and their properties as well, right? So how they are interconnected, how the vectors move from one subspace to another subspace. So the two subspaces belonging to the same vector space, right? These two, these two, row space and null space, these two orthogonal to each other. So you can basically say there is a very popular diagram. This is the diagram which is usually used, right? So here you can see this is the row space, right? A plane. This is the null space. By the way, here the null space is also shown as the plane, but in our case, both the null space and left null spaces are not plane. They are simply lines. Okay, but this is a generic case. This is Rn, right? This is Rn, so and this is Rm. So it could be four-dimensional as well. So you can have a 4 cross 4 matrix where your row space is of dimension 2 and your null space is of dimension 2. So both row space and null space is a plane, but obviously we cannot visualize 4 dimension because of that dimensionality thing. We cannot visualize that. But that could be possible, right? You can have a matrix where a 4 by 4 matrix where the row space and null space both are two-dimensional, hence plane. Same goes for column space and null space. See, you can see that in this diagram they have shown that row space. This is a generic diagram for a m by n matrix. Okay, this is for a m by n matrix. So you can see that the row space is perpendicular. See, the row space is perpendicular, whereas the perpendicular to null space, and the column space is also perpendicular to the null space. The column space is also perpendicular to the null space. Okay. Now, one more thing. In the last lecture, we have studied the dimensions also, right? We have studied the dimension as well. So we know rank. What is rank? The dimension of the column space is rank. That's all. It is also denoted as R. The dimension of the column space is rank. If you see our matrix, this matrix A, for this matrix A, you see that the dimension of the column space, that is this purple plane, and the dimension of the row space, that is this green plane, both is same. Both are two-dimensional. The dimension is 2, right? For both column space and row space, the dimension is 2. So if the dimension of the column space is R, that is rank, so the dimension of row space should also be 2, that is rank. But is it by chance for this matrix A, or is it true for any matrix? So it is true for any matrix. We can see this diagram. You can see that the dimension of row space and column space both is R. The dimension of row space and column space both is R. Dimension is R. All right. So the dimension of row space and column space both is R. That is rank. Okay. Now, if you see this diagram again, if I just show you the rows, the column space and the left null space. Okay, the column space and the left null space. So column space is two-dimensional and the row space is one-dimensional. If you add them, 2 plus 1, what is 2 plus 1? 2 plus 1 is sorry, what is 2 plus 1? 2 plus 1 is 3, and 3 is the dimension of the input vector space, right? This is a 3 by 3 matrix, and the dimension of the column space is 2, and the dimension of the left null space is 1. So you can say that the column space and left null space, they combinedly span or fills the entire input vector space R3, right? Because if you take a linear combination, if you take one vector from column space, and if you take one vector in the row space, sorry, in the left null space, you take a linear combination of them, you will get any vector in this entire R3, any vector in this entire R3 XYZ volume. So I can say that the column space and the left null space, they combinedly fills the entire output vector space, that is Rm. Okay, I can say that. Yes, I can. The thing is, the column space and the left null space combinedly fills the entire output vector space, that is Rm. Okay, they combinedly fills the entire output vector space, that is Rm. So if if the dimension of column spaces are, then what should be the dimension of the left null space? Because the dimension of the vector space is Rm, right? And they both, you can say the linear combination of vectors in column space and left null space fills the entire output vector space. So if the dimension of the column space is R, then the dimension of the left null space should be M minus R. That's how the addition of these two dimensions will give you the entire Rm, right? And we can see this here. The dimension of column space is 2, so the dimension of left null space is 1, because 2 plus 1 is 3, that is the entire Rm. Okay. Now similarly we this is also true for row space and null space, right? This is also true for row space and null space. So this is the row space which is two dimensional, and this is the null space which is one dimensional, right? So you take any vector from the row space and you take any vector from the column space, their linear combination, will fill the entire input vector space, that is Rn. So we can say, similarly, we can say that the row space and the null space, the row space and null space combinedly fills the entire input vector space, that is Rn. All right. So if the dimension of row space is R, then the dimension of the null space is n minus R. All right. Now we come to the fundamental theorem of linear algebra. So it is nothing, it just formalizes whatever we have seen just now. So it basically says that the column space and row space both have the same dimension. So it is not a single thing. It is a it is 2 3 points which it states that column space and row space both have dimension R, that is rank. Okay. The second thing, it says that the null spaces, when I say null spaces, I mean to say both the left null space, the normal null space and the left null space. The null spaces have dimension n minus r and m minus r. And the last and the main thing is, it says that the dimension of the column space plus the dimension of the null space is dimension of Rn, that is n. So this is this is the fundamental theorem of linear algebra in a nutshell. Okay, that is dimension of column space plus dimension of null space is equal to the dimension of Rn, that is n. Okay. Till then, thank you. Bye.